Find out what the natural logarithm is and what this number e is all about. Well, notice I mentioned in that first learning goal something about the compound interest. Well, remember we did a little activity and we've talked about in prior lessons about this idea of exponential growth and specifically about compound interest. So I've written the formula for compound growth here, or I guess exponential growth and decay here. And remember, this is the formula that describes growth or decay by a certain percent over a certain number of time periods t. So if it's growth, we're adding the percent to 1 or 100%, and if it's decay, we're subtracting. So if we were using this formula instead to talk about, say, we were making an investment of money, which we usually call principal. So instead of using A, we might have called this P instead for principal, or the initial amount that you invest. And if something was growing by a percent on a yearly basis, or the T was a number of years, then that would describe how our money grows. Well, then we looked at adjusting that formula to talk about, so some investments of that where we put our money, maybe they might pay interest instead of paying interest one time a year, as this growth formula would take into account, just with T being number of years. Instead, if they paid it, say, every month, then that would happen 12 times every year. And how would we adjust for that? So we looked at the compound interest formula, which is over here in the little yellow box, and I rewrote it a little larger off to the side here. And so remember that the way that worked is that its amount at given time t is equal to P, where P is your principal, also known as your initial investment. And the R part is the annual, or the yield, the percentage that that they're paying you, the annual percentage. So when you see things advertised at 8% interest, then that would be like your annual compounding. They sometimes call it APR. N represents the number of compounding periods. So how often per year do they actually assess your account and pay you interest? So is it quarterly? Is it monthly? So N means number of compounding periods. And T represents the number of years that your money is invested. So again, to see how this compound interest formula works, basically you figure out what they're advertising as the percentage that they're paying per year. So if it's, say, 8%, but they're paying it on a, say, monthly basis, then our N would be 12. So we would have to take that 8% and divide it by 12, because they're only going to pay you 1/12 of that 8% every month. So then the number of times that actually occurs, the exponent, is now not just T, meaning the number of years, but it's T times 12, because that's how many times they actually assess and pay interest. So your interest is earning interest more often. And as we saw in the activity that we did with compound interest and college financing, we saw that with all else being equal, then if you increase the number of compounding periods, it's actually going to increase your amount of money that you have in your account at any given time. So if you compound more often, then you're going to have more money, because then you have more money that's earning interest each time. So the compounding effect is magnified. But in that example that we looked at, that activity, we basically, the most number of compounding periods we really even were able to consider would maybe be compounding every month, so that would be 12 times a year. We looked at quarterly compounding, so that means it happened every quarter, so every 3 months, 4 times a year. We could have looked at for every day, like if they paid daily interest, then our N would be 365, because there's 365 days. But what about if we found an investment where they said they were going to continuously pay you compounding? They were going to just they were going to compound your interest continually, like all the time, like every single second. They were going to be reassessing how much money is in the account, and let's pay them interest based on that fraction of the year, and so on. And so you would think, in theory, that if it was paid continuously, then investment would grow even faster with continuous compounding, and you would be correct. But things like that, your money can't really technically grow continuously. But things in nature, they grow continuously all the time, like your hair, your nails, the trees, the grass, things like that. And so when things grow continuously, and we talk about the multiply, what we're multiplying by, it's not by a certain percent. It actually is growing using what's called the continuous compounding constant, which is E. And this graph over here sort of shows what happens if we keep increasing the number of compounding periods, if we keep increasing the n and out to infinity. Because if something's growing continuously, then the number of compounding periods is really an infinite number. It's just growing all the time. And so we end up getting this horizontal asymptote at the point 2.71828. That's kind of where it's hitting, and that's the number E. And so since that number sort of models this continuous growth, and they approximated at 0.27 or 2.71828, and it's kind of, like I said, like pi. It is a real number, but it's irrational. And so it kind of goes on and forever without any particular pattern, and we approximate it as 2.71828. A logarithm that has a base of E is called a natural log. And it is not, rather than writing it as a log with a base E, okay, instead we use a special notation and we use ln. So that other key on your calculator that you've seen, and I kept mentioning that your calculator does two different bases. It does base 10, which is the common law log, but it also does base E, which is the natural log. And so to distinguish that from the common log, they use the notation ln. And I don't know why it's not NL, because it's natural log, but they use ln instead. And the natural log is really just the inverse of this exponential growth where it's growing, where the base is this 2.718, whatever, it's this continuous growth. It models how things grow in nature. Well, the great thing about the natural log is it is still a logarithm, and all the properties that we know about logs apply for the natural log as well. So we're going to start off first by looking at simplifying expressions with E or with the natural log. So we can use all of our same rules that we know from the prior logarithms that we studied. So example A asks us to simplify the natural log of E raised to the 0.15 t power. Well, this automatically makes me think about, and if I think about writing this in the way I'm used to, it's a log base E of E to the 0.15 t. So that's kind of what I'm thinking in my head. And I remember that there's this power rule that says I can bring that exponent down in front, and it's 0.15 t. So this becomes 0.15 t times the ln of E, or the log base E of E. Well, remember, when the base and the result are equal, that actually means that the value of the logarithm is 1, because E to what power would give you E? Well, this has to be 1. So that actually turns out to be just 1. And so to simplify this, it would just be 1 times 0.15 t, and that's just 0.15 t. And so that's our answer. Turns out to be 0.15 t. Okay, so let's look at example B. Well, this time, let's say I just focused on this part right here. Well, first of all, I know that that I've got a logarithm that's a natural log. It's base E of x plus 1, and there's a number out in front. Well, we've mostly been using this power rule to work by taking the power down in front as a coefficient, but the fact is it actually works in the reverse as well. So I could take this 3 and move it back into the position of the exponent, and if I rewrote this, it would look like this: E to the ln of x plus 1 cubed. Now, why would I do that? Well, remember that when your base of your exponent and the base of the logarithm in your exponent are the same, they essentially sort of just cancel each other out and just leave you with that result of x plus 1 cubed. Well, how about C? Well, this time, if I looked at these two expressions separately and then just added what I got, I think, again, right away of this power rule. So if I take this exponent and bring it down in front for both of these, then this one says 2x times the ln of e, and then plus x times the ln of e. Well, really, remember that the ln of e, the natural log of e, really means it's log base e of e, and that is always going to be equal to 1. So these both equal 1, and all that remains then is just 2x plus x, which makes 3x. So there's some examples of some ways we could use our log properties to simplify expressions with e or the natural log ln. Let's go ahead and turn the page. So now that we've practiced a few of these together, I'd like to have you try example D through F. So using what we know about simplifying logarithms and log properties, simplify in D through F. Pause the video now and tune back in to check your work. All right, so thank you for giving those a try. Be sure to check your answers, and if you miss any of those and you can't figure out what error you might have made, be sure to bring those up when we see each other in class. So next we're going to take a look at what if we could potentially, we talked about this earlier, what if we could potentially find an investment that would pay us interest continuously, that would pay us all the time, like it was always calculating the new interest that we'd earn and putting it in our account and now paying us interest the next time period, which is like immediately after, with our new amount in our account that includes the interest from the prior millisecond. So we're going to be looking at the continuously compounding interest formula. And it's this formula right here. A is equal to P times e to the RT. So let's take a look at what each one of these things represents in the formula. All right, so what about A? Well, A actually represents the amount at a given time t. So the amount that you have at any given current time is A. Now what about R? R is your interest rate that's being paid on the account as a decimal. The P represents the principal or the initial amount of your investment. Or it could be, if you're using this to model even like, say, not just money growth, it could be continuous growth of, say, something out in nature, maybe like how your hair grows or your nails or the grass or things like that. So then that principal, that would be the initial amount that you're starting with. Maybe it could be a bacteria that's growing, you know, and so it's growing continuously all the time. So whatever that initial amount that we have of whatever is growing at the beginning of our situation, that's the P. And T, of course, is the number of time periods, or the compounding periods, or the number of time periods, excuse me. So what about E? Notice I don't have E listed here, and that's because E is not a variable. Okay, E is actually that number that's about 2.718 and so on. So when we see E in that formula, we don't substitute something in for it. That actually is the number 2.718. And when we want to do calculations with it, rather than actually type our approximation of that number in, we can use just like we do with pi, a key on our calculator. So if you'll look at your calculator and look at the ln key, the natural log key, you'll see just above it, one of the functions that's connected with that key is e to the x power. That's the one we're going to use anytime we're doing calculations with e that we have to raise it to the power. Well, there also is an e above the division key on your calculator. If you look over there, that's the one we would want to use if we weren't really raising e to the power and we were just trying to evaluate something that had e with it. So how about an example? So it says, what is the total amount for an investment of $500 invested at 5.25% for 40 years and compounded continuously? So using this formula, we're trying to find the amount A. The principal is the amount of the investment that we started off with. So we started off with $500, and we're going to be multiplying it by E, which is that growth constant, that continuous growth constant. And that's going to be raised to the, let's see, what's in our problem? We've got some things that were given to us that we know. Well, first of all, we know that investment, we saw that was 500. Well, the 5.25 is the percentage that they're going to pay us, the percentage rate. And that as a decimal is what we're going to plug in for R. So if I put that in as a decimal, it'd be 0.0525. That's that as a decimal. And the number of time periods, the T, is 40 years. Well, remember, this whole thing is my exponent. So when I put that in, so that's like I'm multiplying 0.0525 by 40, that's the whole exponent. So now let's go to our calculator and practice putting this in. So please do this along with me. So I'm going to type this in, 500 times E. So I hit the second key and the ln key, and you'll see that brings up the E. It also brings up the little caret sign and the parentheses, so you can put your exponent in. So I'm going to put in 0.0525 times 40. I'm going to close the parentheses, and when I press enter, it'll tell me how much money I would have after 40 years if I could possibly find an investment that would pay me continuous interest at 5.25%. And that turns out to be $4,083.08. That's not too shabby because that means that over that 40-year period, I earned $3,583.08. So that's a significant amount of interest. And in fact, I earned over 7 times as much interest as I actually put in to begin with. When I put in 500, and now the amount of interest I earned was over $3,500. So I earned 7 times in interest alone as what I initially invested. And that might kind of explain why people that are very wealthy stay very wealthy and get even richer, because they have all this money that's earning interest over time. Now that took a long time to earn it, 40 years, granted. But if you had the luxury of just putting money away, stocking it away for 40 years, you'd be in pretty good shape when you go to retire. Now what I did is I decided I want to compare this to a monthly compounding. So I'm going to just do a real quick calculation, and if instead this was paid at a monthly basis. So let's say I started off with my 500. I go back to that other formula for compound interest. And so I'm going to be multiplying that by 1 plus, well, the interest rate as a decimal is 0.0525. If I'm compounding monthly, that would be 12 times a year, so I divide that by 12. And my exponent will actually be 12, which is the number of compounding periods per year, times 40, because that's the number of years. So when I calculated that value after 40 years, I got $4,064.43. So it wasn't that much difference. It was only about $18.65 difference. So, you know, maybe we're not going to be able to go out and find an investment that's going to pay continuously. And if we can find one that pays monthly, we're still in really good shape. But the actual answer to this question is $4,083.08. That's how much we would have if we were using the A equals P times E to the RT formula to calculate growth of $500 at 5.25% for 40 years. Okay, so if the total amount of an investment of $500 is invested for 50 years and compounded continuously was $10,000. Okay, so I invested $500 for 50 years, and at the end of those 50 years I had $10,000. What must have been the interest rate that they were paying me? So when I think about A equals P times E to the RT, I actually am trying to find out what the R would be. I want to know what value this rate must have been, what they were offering me in terms of an interest rate, if that's what turned out to happen, if I ended up getting $10,000 at the end of 50 years. Let's plug the values that we know into the A PERT formula and see how we might solve this. So the amount at a given time, that's $10,000 after 50 years. The initial investment was $500. I was multiplying it by E to the R. That's what I don't know. And I don't know the R, but I know the time was 50 years. Okay, well, so this is, I kind of like to write it with the number in front of the variable. What I'm trying to find is this R value. So if I rewrote that so that I put the 50 first, it would say 50R. So I'm trying to find R, the rate that I was paid. Well, let's see how we might solve this. Well, first thing we would have to do is we're going to get rid of this 500 that's being multiplied by the E. So I'm going to divide both sides by 500. And 10,000 divided by 500 is, of course, 20. So that means that 20 is equal to E raised to the 50R power. Well, now this is just like those problems that we solved when we were doing exponential equations, and we had the variable in the exponent position and we wanted to bring it down. So when we did that, we took the log of both sides. Well, in this case, instead of taking the log of both sides, because the base is E, it's actually smarter if we take the natural log of both sides. And so if we took the natural log of both sides and then we brought that 50R down in front, so we did the ln of E to the 50R, but then we brought it down in front as an exponent, or as a coefficient, we brought the exponent down. Then remember that the ln of E, which that means log base E of E, that's actually just 1. So it turns out that the ln of 20, the natural log of 20, is actually equal to 50 times R. So then the only thing I'd have to do to solve this would be to divide by 50 on both sides. And so by calculating the natural log of 20 divided by 50, that'll give me the R value. So let's see, the ln of 20 divided by 50 is, so we're going to go ahead and type that into our calculator, use the ln key this time instead of the log key of 20, close the parenthesis, divided by 50, and I get approximately 0.0599, and that means as a percent that must have been about 6%. So you can see that we can use a lot of the things we've learned in prior lessons to solve some of these real-life problems, because a natural log really is just a logarithm, and really any of the properties and any of the strategies that we learn to solve exponential equations or logarithmic equations now hold here, where we might be solving exponential equations using a base of E, or solving log equations involving the natural log. Let's go ahead and turn the page. Now, one of the most common applications of the continuous growth formula or the continuous decline formula, which we'll look at decay formula, is when we're studying half-lives of substance. So we're going to be taking a look at some science applications here. And so we actually took that formula for continuous compounding of money, and we kind of just rewrote it and tailored it more towards a real life situation that would involve like substances that occur in nature. And so that's this formula right here, and we're going to talk about what this represents here. So this is just like the A equals P times E to the RT formula, but this time instead of calling it A, we're calling it N of T, and that's this, whatever the amount is at a given time t. So n sub 0, that's a little subscript. That just means the amount of this thing that occurs in nature, that's why they use n, at a given time 0, at time 0, at the beginning. So that's just another way of saying, now t still represents time periods. The k actually represents what's called the decay constant. If K is positive, it would actually be a growth constant. But you'll see in the formula it's got a negative in front of it. And this means we're going to use this to talk about things that are decaying, so are declining over time. And a perfect example of that is like half-life problems. So you may have studied some and heard about half-lives in one of your science classes. And what that means, a half-life is how long it takes for a substance to decay to half the amount that it was to begin with. So let's say I start off with 1,000 of something, and it took, say, 200 years was its half-life. That means after 200 years, I'd have half of that amount, or I'd have 500 of that substance. So that's what a half-life is. It's how long does it take for something to cut in half, to have half the amount that you had in the prior time period. Let's take a look at such example. So plutonium-239. So plutonium-239, I actually looked it up. and at the risk of being like targeted by NSA, because plutonium is actually an isotope that's used for the production of nuclear weapons. So I actually put the definition right here. I took a little picture of it. And it's used to make nuclear weapons. So if I just Googled it, they might think I'm trying to find it to make my own nuclear weapons. I hope that's not the case. But anyway, so it says here that it has a half-life of, and in the problem it says it, and here it says right here on the information I found on the internet too, it's a half-life of 24,110 years. And what that means is after 24,110 years, there'll be half the amount the amount of plutonium that we had to begin with. So I think that's the danger of nuclear weapons. That material sticks around really forever. It will never all be gone, but it takes that many years to just cut the amount in half. So it says, how long does it take for 1 gram sample of plutonium to decay to 0.1 grams? So the first thing I have to do is actually find out what the decay constant is for plutonium. And so following these steps, it says we're going to use this natural decay function, which was this n of t equals n sub 0 times e to the negative kt power. And we actually are going to try to find this k value. That's what we want to know what that is. So first thing we're going to do is we're going to substitute in 1 for n sub 0. So we're going to start off with 1 gram. And we're also going to plug in 24,110 for t, because that's the amount of the half-life. That's how long it takes to get to that. And if we're wanting to know the amount that's half of that, well, what's half of 1 gram? That's going to be a half. So we'll know we've completed a half-life when we have 1/2 remaining. So we put that in for n of t. And then finally, of course, we have the e. And we're looking for the k, and then the half-life is 24,110. So let's see what we can do to solve this. Well, first of all, the 1 that's out in front, that 1 is really not doing anything because it's, 1 times anything is just itself. So this is really just saying e to the negative k times 24,110 equals 1/2. Now, how would we solve something like that? Well, this is an exponential equation, and so we're going to take the natural log of both sides. So, and I'm using natural log because, again, I'm dealing with e, so why not use the natural log? So this is the natural log of 1/2 on this side, and this is, if I bring and use that power rule to bring this down in front, it's negative 24,110 times k, okay, just kind of flip-flop and put the number in front, times the ln of e. Well, remember the ln of e is just simply 1, and so to solve this for k, I need to get rid of the negative 24,110 that's in front of it, so I'm going to divide by negative 24,110 on both sides. So I'm going to jump over to my calculator, I'm going to type in the ln of 1/2, and I'm going to divide it by negative 24,110, and that gives me 2.8749 times 10 to the negative 5th, which is, if I move the decimal back, I have to move it 5 places to the left. That's going to be 0.0000287 approximately. And that's going to be my decay constant. So of course that seems like a very, very small number. And of course it is a very small number. It's decaying very slowly. I mean, it's not even close to 1% even. Because if you move the decimal 2 places to the right, it'd be 0.00287%. So very, very, very slowly, and that's why it takes so many years to cut it in half. That's why it takes that 24,110 years to cut it in half, because it's declining very, very slowly. Now, we still haven't answered the question, because we want to know at what point, how many years would it take for that 1 gram to become 1/10 of a gram? So I know how long it would actually take to be 1/2 gram. It takes that 24,000. But what about how long is it going to take for it to get down to 1/10? So now I'm going to take all this information that I know and plug it back into that formula. So I want to know this time, instead of when it's 1/2, I want to know when it's 0.1. Okay, and I'm starting off with 1 gram sample multiplying it by e raised to the negative k. Well, now I know what k is. It's 0.0000287, and then t is what I'm actually trying to find this time. So this time t is my variable. So now I'm going to kind of work back through that again, where I'm going to solve this exponential equation, but this time I'm trying to solve for t. So I'm going to take the, well, the 1 really doesn't do anything to my formula at all, so I could just get rid of that. I'm going to take the natural log of both sides. I'm going to use the power rule to bring this whole thing down in front. That becomes negative 0.0000287t times the ln of e. Well, we know that the natural log of e is just simply 1, and then this is the natural log of 0.1. So last step to solve for t, I have to get rid of everything that's being multiplied by t, so I'm going to divide both sides by negative 0.0000287, and so dividing natural log of 0.1 by that number is going to give me my answer that I'm seeking, which is the number of years it's going to take to get down to just this 1/10 of a gram. And so when I type that into my calculator, the natural log of 0.1 divided by negative 0.0000287, I get approximately 80,229.4 years, so about 80,229 years. That's a really long time. But it absolutely does make sense. If a half-life is 24,110 years, and this is significantly less than a half, it's going to take a really, really long time. So clearly there's a lot that goes on in these questions related to half-lives, these real-life applications of the natural log. So there is one more example, if you turn the page and take a look at that. And we're going to reserve this one to do in class together. So that way we'll be together as we work through one more example, and we can see if we can figure out, which things are clicking for us, which things do we still